Okay, thank you very much. Can you hear and see my slides?
Yes.
Yes, yes.
Perfect, okay. Oh, thank you very much for this very kind invitation. I would like to say that it's very nice to be here in Ghent, Belgium, but I'm not in Ghent. I'm actually in Sweden, Växjö. So this is the title of my talk, and the plan of my talk is the following. So I will give some motivations and some basic concepts, and then I will come to some, I said, more general lifting results. Well, actually, we will see some easy examples first. This paper, this talk is based on, pardon?
Could you expand your slides a little? I mean,
they are fully expanded in my screen.
Well, also horizontally. I think they were shrinking. Yeah.
I'm sorry. Can you see any difference?
Yeah, here it's better, but now it's too small.
Joachim, if you use this green button at the top.
Screen button.
No, the green button. So instead of closing it, you can expand it. Sorry, at the top of your, here.
Ah, okay. You mean like this?
I think, well.
Yeah, that's much better.
Okay.
Thank you.
Is it? But now I have to make it a little bit more narrow.
Sorry.
Let's see now.
Or otherwise, I think, but I mean, maybe it's fine. But you know, at the top of your file, there are 3 buttons: red, orange, and green. And maybe the green one would go into full screen.
But now it's now it becomes the new method. Just a moment. I cannot.
Okay, sorry.
I tried to open it in another way. Just a moment.
If you can try Acrobat Reader.
I can just take this down a little bit. I just try to. Can you see it better now?
For me, it's good. I don't know, Professor Grupp.
It's good, yeah.
It's good?
Yes, it's good. Much better. Thank you.
Then I try to use this, okay? But I cannot. Sorry. I cannot. I couldn't manage it. I'm sorry. I use it in this way, okay? Hello?
Yes?
Yeah, that's fine.
Yes, fine.
It's okay. I'm sorry for this. The last time it was no problem, but
it's fine.
Okay, now, okay?
Yes.
So what is a lifting? Well, let's say we have 2 spaces V1 and V2. And a lifting is just that you can find a convenient map, T, that takes V1 bijectively into V2s. So that's what we mean with the lifting, okay? And just to give some examples. No, I don't understand why. Use this, okay? So here are some examples. If we take just the usual weighted LP space and have this multiplication operator that takes F into this, it will give a lifting from LPS into LPS minus 0. And you can do similar thing with these Sobolev spaces. But then you have this differential operator instead, this pseudo-differential operator. And also there are some important cases with the Sobolev-Kato spaces where you have both some weights with the x and derivatives in this way. So these are 3 examples on, I would say, easy liftings, and they are very well known. Oh, sorry, I'm used to do that. Well, the point is that, are there other situations? Well, of course, if there are some kind of weighted spaces where you have a mixture between the differential operators and the multiplication operators of this kind, let's say Fourier multipliers, then the situation becomes more tricky. So in order to prepare this, we need some concepts. We need a Fourier transform. We need a short-time Fourier transform, defined in this way. So then we also should look at the pseudo-differential operators. In this situation, it is convenient to look at Weil operators. The main idea with these lifting results that we want to look at is that these liftings, they should be pseudo-differential operators. Because when using pseudo-differential operators, we have how to say, a big machinery of theory, composition results, etc. So that's the main point. But we shall also look at that we can look at as a special case of pseudo-differential operators, the Toeplitz operators. And I come to them right now. So they are defined in this way. There are several names of these kind of operators. Another name is localization operator. Important is that we can include these Toeplitz operators as we can view them as a special case of pseudo-differential operators, because we have this equality here, where you have to convolve the Toeplitz symbol with this Wigner distribution. Okay. We also shall look at these lifting properties on modulation spaces, and then we shall look at weighted modulation spaces. This is weight with a positive function, etc. And we want that this weight should be moderate. So this is a condition that it is moderate. This positive function V should exist such that we have this kind of inequality. We also let PE be the set of all moderate weights on RD. But we also need some subclasses. And one can actually prove, it's not difficult at all, that if we have a moderate weight, then it must fulfill an inequality of this kind for some R greater than 0. We also let this PE0 be the set of all such omega, such that this inequality here holds for every R greater than 0. This notation here with this kind of approximate inequality means that we have a hidden constant here. This hidden constant in this case depends on R, of course. So if R is chosen smaller, then we should choose this constant here. Perhaps we need to choose it larger. And we also let P without any E or 0 be the set of all such weights, such that we have polynomial type moderateness here. So this should be true for some n greater than 0. And here still, this is the bracket function that we defined in another slide. We want to present lifting properties for spaces that are not in the usual distribution theory. We shall actually look at space if ultra distributions. One way to define the Gelfand-Schilot space, sigma 1 and S1, is that we should have all bounded functions, but also the Fourier transform should be bounded such that this is true. We have this inequality and this inequality. In sigma 1 case, we have that this should be true for every r greater than 0. And for S1, it should be true for some r. It can be shown that this is equivalent, that F must be smooth and satisfy this kind of condition here. And we can notice that this is some kind of analyticity condition. So, and it, by the definitions, it then follows that we have this kind of inequality, this kind of inclusions between the Gelfand-Shiloh spaces and the Schwarz space. And the dual or distribution spaces are defined in a similar way as for the usual distributions in the ordinary distribution theory. Okay, now we come to modulation spaces. So this is introduced by Feischinger, 1983, and it consists of all F in sigma 1 prime now, such that this kind of norm we have here is bounded. And phi here is a fixed so-called window function, and it should be in this sigma 1, but it's not allowed to be 0 here, because then we have just 0 here. What is important is that these spaces are independent of the choice of window function phi. And we can also, in the case that we take the weight of this more smaller set, then one can show that these modulation spaces, they are states between S1 and S1 prime. They are also quasi-Banach spaces, so they are complete spaces. And if we have a polynomial moderate weight, then we are in the ordinary distribution theory. Some properties, well, we can first of all get the usual, the most common Sobolev space, as well as perhaps the most common L2, weighted L2 space. We also have a big scale of Fourier invariant spaces, and we also have, how to say, natural duality properties. But we also have a nice property that if we increase the parameters P and Q, we increase the spaces as well. And also we have several other types of properties. We can see. Pardon? For example, we can discretize them by using Gabor frames. Okay. So here are also some other things that is needed. We shall actually look at some symbol classes for our pseudo-differential operators that is adjusted to these modulation spaces. This means that in contrast to the usual symbol classes, we also put some kind of gevrey conditions here in a similar way as for the Gelfand-Shiloh spaces. On the other hand, in contrast to the ordinary theory of pseudo-differential operators, we allow our symbols to grow more than polynomially, sub-exponentially in our situation. Okay. So liftings again. We start with the classical results from 2002, where Boggiato, Cordier, and Gröchnig, they considered Toeplitz operators with symbols of this bracket function here. Notice that this omega s depends both on x and psi. So it is so it takes variables on the phase space. And then we define this Shubin space as in this way. And they proved that this Shubin space agree with this modulation space. And also that this Toeplitz operator lifts this modulation space into L2. This is a more hard lifting result, because here we have a symbol class where you cannot split up it into separate. It's not a symbol of split form. It's a symbol where these x and xi variables are mixed. So then we have a big interactions between multiplications and differentiations. This result was generalized by myself and Boggiato 2005 in this way. And we can see here that we have extended the class. We have now more general symbols. On the other hand, we still have some gains when we differentiate the symbols. And then we were able to prove that this Toeplitz operator lifts this MPQ omega 0 into this unweighted modulation space. This condition here was rather annoying. But in a paper by myself and Gröchenig from 2011, we were able to extend this result we have here by just removing. So we were able to remove this condition here. And at the same time, we found another type of lifting property, actually taking the theory also into ultra-modulation spaces. With modulation spaces now could be, I'd say, outside the usual distribution theory. So we have now symbols in PE0 here instead of P. This means that our weights, they are able to grow or decay sub-exponentially. But we needed a restriction. To get similar type of lifting result as here, we needed actually that our symbol, weight omega should be radial symmetric in each phase space variable. This was, of course, an annoying restriction, and we were thinking a lot. Couldn't we remove this condition? But at least me and Charlie Gröchenig, we were not able to get rid of this, this condition here with the methods that we were using in that paper. But in the end, it could be a happy end of this story, because by recently, myself together with Sandro Coriasco and Ahmed Abdeljawad, we were able to actually remove these kind of restrictions we had in this paper by Gröchenig from 2013. So this is somehow the ultra-distributional version of the result we have from 2011. And if we go back to the paper I had in the first slide, we can see that the analysis was rather longer compared to the other papers. This paper was about 60 pages, and very much because we needed to develop, how to say, the theory for pseudo-differential operators in the context of Gelfand-Shiloh spaces, even more than before. Still, it's based on several other papers on this theory. Okay. The approach to prove 3 is similar to this paper, but we needed some more development of the theory of pseudo-differential operators. I will come to that. Okay. If we now look at the arguments of the proof in the paper by myself and Charlie from 2011. Well, first, from the general theory of pseudo-differential operators on modulation spaces, we could conclude that any such operator is continuous from this modulation space into that one. Then we could also prove that this Toeplitz operator really lifts m2 theta into m2 1 over theta, where theta is this omega 0 up to power 1/2. So also here, let T1 be the inverse, because then it's a bijective map. How to get this lifting? This is not difficult to get, actually. The main argument is the following. We start with this norm of M2 theta. And this is the same as you take this. This follows on the general theory of modulation spaces. So we can write this in this way. This is a Hilbert space, actually, this M2 theta. And then we can write this explicitly on this form. But theta squared is the same as omega 0. So now we can rewrite this of this form. I think it should be an F here. No, it should be an G here. I'm sorry, that is a misprint here. And now, by the definition, this is the same as what we have here. And now we actually have that M2 of theta, if we instead of using this form, we are using L2 form, then one can prove that the dual of M2 theta is M2 of 1 over theta. So this here is by definition about the same size of this. So this shows that this here is essentially the same as this norm here. And then it follows by easy argument that this really becomes a bijective map from here into here. By Bonnet and Sherman, they wrote an important paper on the Hermann de Weil calculus. They had a result that if you have a symbol in this space and you have a symbol here, then, if you have this space and this symbol class, then there exists A and B such that they are corresponding Weil operators are inverses to each other. And now by 2 and 3, it now follows that if we form this composition here, then this is bijective on L2. And by symbolic calculus, it's also, one can see that this C really belongs to this S0, 0, 0. And this implies that, and S0, 0, 0 is also a Wiener algebra. So the inverse of this op C is of the same type, of the same class, okay? So this implies that T1 is given in this way with a symbol in that space. Remember now that T1 was the inverse of this operator here. And now from these properties, it actually follows that both of these operators here now are continuous in this way. And by 2, we can also see that they are, these kind of things are identities on the Schwarz space. And then they are also the identities on S prime. And therefore, by taking the good restrictions, it follows that these operators here are not only continuous, but they are actually inverses to each other. And this shows that this TP of omega 0 is a lifting. Okay. Now, if we look at our recent result, we ask which kind of steps here still works in this theorem too. First of all, the arguments in 1, they are fine. 2 also are fine. They work in the same way as for the alpha distributions. 3 needs to be replaced by the following. There are now corresponding, gevrey symbols in gamma 1 of theta. This corresponds to this, of course. And a B here, such that these here are inverses to each other. Now it's not enough with S prime. These operators are not working well in S prime. It must be their identity operators on the corresponding gevrey distribution space. Four works fine if we now replace this S000 with gamma 010. But we still need that 3' is proved. 5 also works fine, provided this 3' is proved. So a very big step here, a big issue, and this was a big part of the paper, was actually to prove 3'. Okay, so how to do that? So this is now a big theorem we need to try to view. And I will of course not present the whole proof, I will only present some steps here, some ideas that we followed. So the main idea was actually to expand in the theory of pseudo-differential operators with symbols in these gevrey classes in the lines of what Bonnet and Germain did. For example, we had to find some analogies to this confined symbol approach. So what we did was that we localized A and B in this way. In contrast to the Bonnet-Germain, we have Bonnet-Germain dealt with the very general Hermann-Weyl calculus, where the symbol classes are parameterized with weight functions and a metric G. This G is very simple in our situation. It's a constant metric. So this is what we made this reduction to confined symbols. By integrating, we can actually get that this kind of Weyl products, if we have symbols in these two classes, satisfy something like this. Also, the other thing was to deduce in Beal's characterization of these symbol classes, these operator classes. This means that we made suitable estimate of powers of commutators of such operators with operators having linear symbols. And then we come to a big part, solving a symbol-valued evolution equation. This means that the equation we considered is this one here, where we have A here is it depends on the parameter t, and is then, with respect to t, a symbol-valued function. And this is very simple. Well, a simplification, a simplified explanation, but we had to look at the solution. And actually, by solving this problem, taking t equal to 1, and choosing A0 to be 1, then we actually got this 3', the existence of these A and B. Okay, 2 examples. By combining this Lifton result with Fredholm theory, we can, for example, see that it's easy to see that this pseudo-differential operator is bijective from this space into that space. But now we can also get the corresponding Toeplitz operator is bijective. We can also, since we now are allowing symbols to grow sub-exponentially, we could also consider this kind of symbol here. And it follows at once from our result that this is bijective from this space into that space. But we can also use approximations between Toeplitz operator and pseudo-differential operators. And we cannot be sure that this pseudo-differential operator, at least from our result, is bijective, but at least it will have the index 0 and so on. So this was everything that I had in mind. So I thank you very much for your attention.
Thank you very much for this very nice talk. So we are open for questions. So are there any questions?
I have one question for,
yes,
but it's about the last slide, about the index of Topliss. This operator has index 0. Yes, usually for Topliss operator, the index is some like the window number of the symbol, but here how can interpret this that the index of this operator is 0?
You mean?
Yes, in the classical index theorem for Topliss operators, the index of one Topliss operator is the window number of the symbol. Yes.
Yeah.
I mean, here, how one can interpret this the index of this Topliss operator?
I mean, in this situation, we yes. have. I mean, if you look here, the Topliss operator itself is bijective. So then it must have the index 0. I don't know how to explain this more actually.
Sorry, maybe.
So for sure this has the index 0, and yeah.
Okay. Yes, it's true. Okay, thank you.
Other questions or comments?
And you can use some in closeness results, right? For this. After this, you can in principle state something about inverse closeness.
Yes, I mean, you mean with the index result or with the bijectivity or?
Bijectivity.
Yeah, I mean, to prove it, of course, the arguments I showed how to prove this step 2 before. Of course, there I just put the norm estimate, but of course one need some kind of a closeness result there. But I mean, we are mapping. Well, these. I mean, of course, these mappings, they are continuous in both directions.
Okay, Michael?
Yes, okay, this is, yes, okay. Yeah.
Okay, so are there...
May I ask a question?
Yes, please.
So Joachim, you said when you defined these confined symbols, there were some technical issues or it was rather complicated. Could you elaborate a little bit on that? Maybe I'm just curious.
Yeah, I mean, I can go back to the slides here, okay?
Mm-hmm.
I mean, so what we did was that we needed some different kinds of estimate of this form. I would say that this one is the most important one.
Mm-hmm.
So what you can, in the whole theory is that, I mean, when you perform when you discuss different kind of, for example, continuity and composition properties, I would say that this kind of estimate you have here contains more information than when you have integrated up everything and you just have all the symbols, okay? Because this shows somehow that if you have localized A at the point Y and B at the point Z, okay? A big question is, okay, if you now compose this, what can you say about this? What kind of bounds can you get about the symbol? And And this is the bound. So this actually shows that if y and z are very far away from each other, then this factor here becomes very small.
Mm-hmm.
And if you look at the usual, so in for example, paper by Bonny and Germain, and also other papers by Bonny and collaborators, I would say, they had similar type of estimate, but of course of polynomial growth. But here we need exponential. I'm sorry, 1 over polynomial decay, I would say. But here we need exponential decay. But of course, the big problem here was to work with this symbol-valued evolution equation. To solve this and get the right type of estimates, it needed a lot of effort, especially because we had. I mean, we were basically solving this as an ordinary. I mean, if you look at a classical proof of when you want to show uniqueness of a solution to an ordinary differential equation. But we had to use a lot of other type of estimates as well to see, for example, that it works fine with these kind of that we can get in the end right type of factorials, etc. So that's what we needed.
Thank you very much.
Thanks a lot. So if there is no more questions, so let's thank Joachim again for this very nice talk.